Right now, roughly 93 million miles from where you are sitting, a ball of plasma is releasing more energy every single second than humanity has consumed across its entire history. It has been doing this for about 4.6 billion years, and for most of that time we barely understood any of it. We could see its light. We could feel its heat. On the rare occasion that the moon slid perfectly between the sun and Earth, we caught brief, terrifying glimpses of its outer atmosphere roaring into space like a ghostly crown. But the actual mechanics, the deep physical story of what the sun is doing from its surface all the way up through its outer atmosphere, that remained genuinely mysterious for most of human history. Even today, some of the most fundamental questions about our own star are only now being answered. This is the story of how we finally started seeing the sun clearly. Not with naked eyes, not through filtered telescopes aimed at a bright disk, but with instruments capable of peeling back its layers one by one, separating temperatures, isolating processes, and watching in real time as things happen that no human ever witnessed before. And some of what we found is deeply strange. The surface behaves like boiling soup. The atmosphere above it gets hotter as you move further away from the heat source below, which is the opposite of everything physics would suggest. Massive waterfalls of superheated plasma fall upward and then back down. Billion-ton clouds of charged particles are flung into space faster than you can imagine, and sometimes they come straight at us. The deeper we look into the sun, the more we realize it is not a simple furnace. It is an extraordinarily complex machine, and the tools we now have to study it are unlike anything that has ever existed before. One of the most important of these tools is the Solar Dynamics Observatory, launched in February 2010. It stares at the sun without blinking, capturing images every 12 seconds across 10 different wavelengths of light. Most of those wavelengths fall in the extreme ultraviolet range, a part of the spectrum completely invisible to human eyes, but one that reveals entirely different layers of solar material at entirely different temperatures. Different wavelengths act like different lenses, each one tuned to highlight plasma at a specific temperature, which means each one effectively shows a different altitude in the solar atmosphere. When you layer those images together, you stop seeing a flat glowing disk and start seeing structure, depth, and motion that was completely hidden before. Then there is the NSF's Daniel K. Inouye Solar Telescope, which began producing science images in the early 2020s and immediately changed what we thought we could see. It has captured the sharpest images of the solar surface ever recorded, revealing features as small as 21 kilometers across on an object 1.4 million kilometers wide. To put that in perspective, that is like being able to spot a single city block on an object so large that 1 million Earths could fit inside it. And then there is NASA's Interface Region Imaging Spectrograph, known as IRIS, which focuses specifically on the transition zone between the surface and the outer atmosphere, and can capture rapid, high-resolution movies of plasma behavior at timescales that previous instruments simply could not match. Together, these tools have given us something we have never had before, a detailed, layered, continuous view of our closest star. And what they have revealed is one of the most dramatic stories in all of modern science. Let's start at the visible surface and work our way up, because the journey through the solar atmosphere is one of the most surprising in all of astronomy. The layer of the sun we can actually see with our eyes, assuming you use proper solar filters and do not spend the rest of your life blind, is called the photosphere. It is not a solid surface. It has no ground to stand on. It is entirely made of plasma, which is essentially a gas so hot that electrons have been stripped away from their atoms, leaving behind a charged, energetic, fluid-like state of matter that behaves unlike anything we encounter in everyday life. At first glance, the photosphere might look relatively smooth, especially in older photographs taken with lower resolution instruments. But look closely with modern telescopes and the surface is anything but smooth. It is covered in a constantly shifting, constantly churning pattern that looks a little like the top of a pot of thick oatmeal at a full rolling boil. These individual cells of motion are called solar granules, and they are the visible tops of enormous convection columns rising from deep inside the sun. Each granule is a single convection cell. Hot plasma rises through the center of the granule, releases its energy as light, cools down slightly, and then sinks back into the interior around the edges. A typical granule is around 1,000 kilometers across, which means a single one of these boiling cells is roughly the size of the state of Texas. And the entire photosphere is tiled with them, millions of them at once, each one living for about 8 to 20 minutes before dissolving and being replaced. The photosphere is never the same from one moment to the next. It is alive with continuous motion. What is extraordinary about recent analysis of this granulation is that scientists have detected supersonic fluid movements hidden within it. The overall motion of granules, the slow rise and fall of plasma, happens at speeds well below the local speed of sound. But embedded within that flow, particularly in narrow lanes and regions of strong magnetic activity, the plasma can be moving fast enough to break the sound barrier. On the surface of the Sun, in the quiet-looking layer we see every day, there are supersonic currents most people have never heard about. Then, there are sunspots. These are the dark patches that occasionally appear on the photosphere, visible even through basic solar telescopes, and they have fascinated observers for centuries. What we now understand about them is far more detailed than anything previous generations could have imagined. Sunspots are regions where intensely concentrated magnetic fields punch up through the photosphere. These fields are so strong that they essentially trap the plasma in place, restricting its freedom of motion and preventing the normal convection process from operating. Because that convection is what delivers heat from below, a sunspot is a region where the heat delivery has been partially blocked. The result is a patch that is significantly cooler than its surroundings, around 4,000 degrees Celsius compared to the roughly 5,500 degrees of the normal photosphere. They look dark not because they are cold in any absolute sense, but because they are so much cooler than everything around them that they emit far less light by comparison. Each sunspot has two visible zones. The very dark center is called the umbra, and the lighter, fibrous surrounding region is called the penumbra. Recent fractal analysis of these structures has revealed something genuinely interesting about what those zones represent physically. The fractal dimension of the umbra is around 2.09, which indicates a high degree of structural complexity. That complexity exists precisely because the magnetic fields there are so strong that plasma is heavily confined and restricted. When you trap plasma under intense magnetic pressure, it carves out complicated, intricate structures because it has nowhere easy to go. The penumbra, by contrast, has a fractal dimension around 1.72, indicating a somewhat less complex but still richly structured region. The difference reflects the fact that magnetic fields in the penumbra are weaker and less organized, allowing plasma more freedom and higher local temperatures, which produces a different kind of complex geometry. Sunspots do not appear randomly. They appear in clusters linked to the Sun's magnetic cycle, which runs approximately 11 years from one peak of activity to the next. As we have recently entered a particularly active period known as Solar Cycle 25, the number and intensity of sunspot groups has been notably high, setting some records not seen in decades. That matters enormously for everything that happens above the photosphere, which is where things start getting genuinely strange. Move upward from the photosphere and you enter the chromosphere, a layer that sits just a few thousand kilometers above the surface but behaves in ways that initially seem to make no sense at all. The chromosphere is thinner and more dynamic than the photosphere, and for a long time it was only clearly visible during total solar eclipses, when it appeared as a thin reddish ring around the darkened solar disk. Today, we can observe it in exquisite detail using specialized wavelengths, particularly the hydrogen alpha wavelength of 656 nanometers, which glows red and highlights the chromospheric plasma beautifully. What you see when you look at the chromosphere in detail is one of the most energetic, chaotic environments in the solar system. The entire layer is filled with what appear to be spikes or jets of plasma shooting upward from the surface. These are called spicules, and they are one of the most important and most puzzling features of the entire solar atmosphere. A spicule is essentially a narrow column of plasma that erupts from the chromosphere and rises upward at extraordinary speed. Each one travels at up to 100 kilometers per second, which is roughly 282 times the speed of sound. They extend to lengths of around 10,000 kilometers, which means a single spicule is almost as tall as Earth's diameter. They live for somewhere between 5 and 10 minutes, and at any given moment there are approximately 10 million of them active simultaneously across the entire Sun. For decades, the physical mechanism that drives spicule formation was one of the most actively debated problems in solar physics. The challenge was explaining how magnetically charged plasma could rapidly escape the sun's magnetic grip and shoot upwards so violently and so frequently. Standard models of the chromosphere simply could not reproduce the spicule behavior observed in real data. The breakthrough came in 2017 when researchers combined high-cadence observations from IRIS and the Swedish 1-meter solar telescope with year-long supercomputer simulations. What they found was that the missing ingredient was something that had long been excluded from standard solar models: neutral particles. In the lower chromosphere, not all particles are fully ionized. Some remain electrically neutral. Those neutral particles behave differently in a magnetic field. Specifically, they can slip through the magnetic field in a way that charged particles cannot, creating the buoyancy and pressure gradients needed to drive plasma explosively upward. Including neutral particles in the simulations finally produced spicule behavior that matched observations, solving a problem that had resisted resolution for generations. More recently, high-resolution observations using the Good Solar Telescope revealed another piece of the puzzle. Spicules tend to emerge just minutes after localized patches of reversed magnetic polarity appear on the surface below them. When the magnetic field in a small region suddenly flips direction, relative to its surroundings, the resulting stress on the field appears to trigger the eruption of a spicule above it. There is a direct, observable cause and effect relationship between what happens at the surface and what erupts above it. And advanced multidimensional simulations have also confirmed a strong connection between spicules and slow magnetohydrodynamic shocks that travel upward through the chromosphere, steepening in strength as they enter less dense layers and effectively flinging plasma outward along their wavefronts. The importance of spicules reaches beyond their own visual drama. They are increasingly believed to play a role in delivering material and energy upward into the higher solar atmosphere. Every one of those millions of jets is carrying plasma and electromagnetic energy upward, and the cumulative effect across the entire sun adds up to something enormous. Understanding them is not just an interesting exercise in solar physics. It is part of understanding why the outer atmosphere of the sun behaves the way it does. And the behavior of the outer atmosphere is one of the most astonishing and long-standing mysteries in all of astrophysics. Above the chromosphere there is an extremely thin interface layer called the transition region, stretching somewhere between 100 and 1,700 kilometers thick. In that narrow band, something extraordinary happens to the temperature. Moving upward through the chromosphere, you start at a temperature of roughly 10,000 degrees. By the time you exit the transition region and enter the corona, the temperature has exploded to somewhere between 1 million and 3 million degrees Celsius. In some localized coronal regions above active areas, temperatures can reach 10 million degrees or higher. This is completely counterintuitive. You're moving away from the heat source, which is the nuclear fusion happening in the solar core. By every straightforward expectation, things should get cooler the further you go from the energy source, just as moving away from a campfire makes you feel less warm. But the corona defies this. It is not just warmer than the photosphere, it is hundreds of times hotter. This is called the coronal heating problem, and it has puzzled scientists since the 1940s when the extreme temperature of the corona was first confirmed. Modern observatories have made enormous progress in narrowing down what drives this heating. The Solar Dynamics Observatory, using specific wavelengths that highlight plasma at 600,000 Kelvin, at 1 million Kelvin, and at temperatures above 2 million Kelvin, allows researchers to map where heat appears and disappears in the corona across time. By watching how specific regions in the corona transition from hotter to cooler wavelengths over 12-hour observational periods, scientists have been able to determine something important. Coronal heating is not steady. It is impulsive. It comes in rapid bursts. Two mechanisms appear to be particularly important. The first involves something called nanoflares, which are essentially tiny magnetic reconnection events happening continuously throughout the corona in enormous numbers. Each individual nanoflare is too small to detect directly with current instruments, but the cumulative energy delivered by billions of them happening simultaneously could plausibly account for the total observed heating. The second mechanism involves Kelvin-Helmholtz instabilities, which are wave-like rolls that form at the boundaries between plasma flows moving at different speeds, similar to how waves form at the interface between wind and water. These waves generate turbulence and friction as they propagate through coronal plasma, converting their energy into heat. Neither of these mechanisms is fully confirmed as the dominant driver, and it is likely that both contribute in different contexts. But the crucial insight from modern data is that whatever is heating the corona does so in short, powerful, repeated impulses rather than through any continuous steady input. The corona is not being slowly warmed, it is being constantly hammered with brief intense bursts of energy. The Inouye Solar Telescope has pushed this research further than anything before it. Its ability to resolve coronal features as fine as 21 kilometers across has allowed scientists to see individual coronal loops, which are arched structures of plasma trapped along magnetic field lines, at a level of detail that was previously impossible. These thin coronal loops are among the fundamental structures of the solar corona, and understanding their thermal properties and lifetimes is central to solving the coronal heating problem. Every new image from Inouye essentially adds data points to models that are still being refined and challenged. All of that stored magnetic energy in the corona does not just heat things quietly. Sometimes it releases with catastrophic force. These sudden, explosive releases are called solar flares, and they represent the most powerful events in the solar system that do not involve a comet strike or a planetary collision. A solar flare begins when magnetic field lines in the corona become twisted, stressed, and eventually forced into contact with neighbouring field lines of opposite polarity. When that happens, the field lines snap and reorganize in a process called magnetic reconnection. The stored magnetic energy, which can range from 10 to the power of 28 ergs at the low end to 10 to the power of 32 ergs at the high end, is released almost instantaneously. For comparison, the lower end of that range is roughly equivalent to the total energy output of the Sun across several hours. The upper end represents more energy than humanity could generate in millions of years. When that energy releases, it heats the local plasma in the corona to around 20 million Kelvin almost immediately. High-energy electrons are accelerated downward along magnetic field lines toward the denser chromosphere below, arriving there with enormous kinetic energy. When those electrons slam into the denser chromospheric plasma, the energy is deposited so rapidly that the local material heats up in a way the chromosphere cannot absorb gradually. The result is a violent, explosive upward expansion of chromospheric plasma, a process called chromospheric evaporation. This evaporated plasma, now at temperatures between 20 and 30 million Kelvin and densities around 10 to the power of 10 particles per cubic centimeter, rises rapidly into the overlying corona and fills the magnetic arcade structures above the flare site. These filled arches of trapped plasma are called post-flare loops, and they can remain visible for hours after the initial explosive event, slowly cooling from their extreme temperatures as the system gradually recovers. The three-phase structure of a solar flare, a quiet pre-flare phase, a sudden explosive impulsive phase, and a long gradual recovery phase, is now well understood in broad strokes, though the fine details of each phase continue to be studied with modern instrumentation. Solar flares are frequently accompanied by something even more physically consequential: coronal mass ejections, commonly abbreviated as CMEs. While a flare is essentially a burst of electromagnetic radiation, a CME is an actual physical eruption. It is a bubble of magnetized plasma, potentially containing billions of tons of solar material, hurled outward into interplanetary space at speeds that can range from a few hundred kilometers per second on the slow end to over 3,000 kilometers per second for the most extreme events. High-resolution observations from the Solar Dynamics Observatory have revealed the formation process of CMEs in detail. Before the eruption, the site often shows the formation of a magnetic flux rope, a twisted, coiled structure of magnetic field lines that looks roughly like a slinky standing on end, illuminated by the glowing hot plasma flowing along its length. The flux rope stores increasing amounts of magnetic energy as the field lines continue to twist. When the rope's connection to the surface is severed by magnetic reconnection, the structure explosively expands outward, carrying its entwined plasma with it into the heliosphere. When a CME is directed toward Earth, it typically takes between 1 and 4 days to cross the 93 million miles of space between the Sun and our planet. When it arrives, it interacts with Earth's magnetosphere, the magnetic cocoon that surrounds our planet, compressing it on the side facing the Sun and stretching it on the night side. This interaction drives a geomagnetic storm, and the severity of that storm depends largely on the orientation and strength of the magnetic field embedded in the incoming CME. The consequences of severe geomagnetic storms are not theoretical concerns. During the Carrington event of 1859, the largest geomagnetic storm in recorded history, telegraph networks across North America and Europe were disrupted. Some telegraph operators reported receiving electrical shocks. Auroras were visible as far south as the Caribbean. If an equivalent event struck today, the consequences would be vastly more serious. Satellites in low Earth orbit would experience rapidly increased atmospheric drag and potentially deorbit prematurely. GPS timing signals, which underpin everything from financial transactions to aviation navigation, would be severely degraded. High-frequency radio communications used by aviation would be disrupted over polar routes, and perhaps most alarmingly, the induced currents that a severe geomagnetic storm can drive through long, ground-based conductors could damage or destroy transformer equipment in major power grids. Some engineering analyses have estimated that recovering from a Carrington-scale event today could take months to years and cost trillions of dollars. This is why solar physics research is not simply an academic pursuit. It is a practical matter of infrastructure security. Not all solar activity manifests as violent eruptions. Some of the most visually spectacular features of the corona involve a different process entirely, one where plasma that should have no business surviving in the corona's million-degree environment somehow manages to form, cool dramatically, and then fall back to the surface in enormous glowing streams. These structures are called solar prominences when they extend beyond the solar limb and are viewed against the dark backdrop of space, or filaments when viewed against the brighter solar disk. They are enormous volumes of plasma that are roughly 100 times cooler and 100 times denser than the surrounding corona. By all rights, the hot corona should immediately evaporate them, but they are supported and insulated against their hot surroundings by a complex web of magnetic field lines that essentially cocoon the cool material and hold it suspended high in the corona, sometimes for weeks or even months at a time. When the magnetic structure supporting a prominence becomes unstable, the whole thing can erupt outward, contributing material to a CME. But in their quiescent state, prominences are beautiful examples of magnetic confinement operating on a solar scale. Closely related to prominences is a phenomenon called coronal rain, and it is one of the most visually striking things that modern solar telescopes have captured. During the gradual phase after a solar flare, the post-flare loops are filled with hot plasma cooling from their initial temperatures of tens of millions of degrees. As they cool, they pass through a phase of thermal instability where the cooling accelerates catastrophically. The plasma drops from temperatures above 1 million Kelvin to roughly 10,000 Kelvin in a very short time, a process called catastrophic cooling. At 10,000 Kelvin, the plasma is dense and relatively cool by coronal standards, and it begins to condense into discrete clumps. Those clumps, pulled by the sun's gravity along the guiding tracks of the magnetic field lines, fall back downward toward the surface, glowing brightly in the extreme ultraviolet wavelength of 304 angstroms. The result looks exactly like what the name suggests: rain. Streams of glowing plasma, each clump perhaps a few hundred kilometers across, streaming downward along the arched shapes of magnetic field lines back to the solar surface. It is rain on a solar scale, and it is genuinely beautiful to watch in time-lapse footage. For years, one aspect of coronal rain puzzled astronomers. The cooling process, according to standard models, should take considerably longer than observations showed. The plasma was cooling and condensing faster than the math predicted it should be able to. A 2025 study resolved this discrepancy by identifying the key missing ingredient. The elemental composition of the coronal plasma is not constant over time. Specifically, elements like iron vary in their abundance as the corona evolves. Standard models had assumed a fixed composition throughout the cooling process. When the models were updated to account for shifting elemental abundances, particularly the variations in iron content, the predicted cooling timescales matched the observed rapid condensation. The sun was essentially changing its own chemistry as it cooled, and that change accelerated the whole process. The behavior of coronal rain is also shaped by the local magnetic environment it falls through. In regions called supra-Arcade fans, which form in current sheets above flare sites where the magnetic field is relatively weak, the cooling plasma behaves turbulently, forming tangled, meandering threads that twist and wander rather than following neat paths. But when that same material descends into the underlying arcade structure, where magnetic fields are stronger and more organized, the behavior changes completely. The plasma is strictly guided along the field lines, forming the clean, structured streams of coronal rain that look so distinctive in solar images. The magnetic field is simultaneously the track, the guide, and the sculptor of the material falling through it. While all of this explosive and dramatic activity is happening in magnetically complex regions, there are other parts of the corona that look strikingly different. These are called coronal holes, and they appear as large, dark patches in extreme ultraviolet and X-ray images of the Sun. They look dark because they contain less plasma and less heat than surrounding regions, not because they are empty, but because they are open. In most of the corona, magnetic field lines arch upward from one region of the photosphere and curve back down to connect to another nearby region, like bridges made of magnetism. Plasma trapped on these closed loops stays in the corona, heating and glowing brightly. But in coronal holes, the magnetic field lines do not loop back. They extend outward from the Sun and continue indefinitely into interplanetary space without returning. Without the confinement of a closed loop, plasma is not trapped. It flows outward along those open field lines and escapes the Sun entirely as the solar wind. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the Sun in all directions at all times. It fills the entire heliosphere, which is the vast bubble of space carved out by the Sun's influence, extending well beyond the orbit of Neptune and Pluto. The solar wind is not uniform. Coronal holes produce what is called the fast solar wind, which travels at 500 to 800 kilometers per second. The slower solar wind, emanating from other regions, including the boundaries of active regions, moves at around 300 to 400 kilometers per second. As the Sun rotates, high-speed streams emitted by persistent coronal holes sweep through the solar system like the beam of a rotating sprinkler. When a fast stream catches up with a slower stream ahead of it, the two interact, compressing the plasma at the boundary into what are called corrotating interaction regions. These interaction regions are surprisingly effective particle accelerators, and they also modulate the flux of galactic cosmic rays reaching the inner solar system. When high-speed solar wind streams from equatorial coronal holes sweep past Earth, they frequently generate geomagnetic storms. These are often milder than CME-driven storms, but they are far more predictable because the coronal hole structure is visible days before the stream arrives at Earth. Something called the Russell-McFerran effect means these storms are stronger near the equinoxes in March and September, when the geometry of Earth's orbit and magnetic field is particularly favourable for transferring energy from the solar wind into the magnetosphere. Every aspect of the solar wind, its speed, density, temperature and magnetic field orientation, has direct consequences for Earth. It shapes our magnetosphere, drives auroras at the poles, affects satellite drag, and influences the radiation environment for both astronauts and electronics in space. And the primary driver of all of it, the engine behind the solar wind, is the structure of magnetic fields on the Sun that we can now observe in detail with modern instruments. This is what is so remarkable about where we stand today in solar science. A generation ago, we watched the Sun as a static bright disk with the occasional dark spot. Now we can see individual structures 21 kilometers across on its surface, watch plasma jets erupt at hundreds of times the speed of sound, observe magnetic ropes forming and snapping in real time, watch rain fall from the corona back to the surface, and track the storms that leave the Sun and arrive at Earth days later. We have built instruments that can separate the Sun's atmosphere into layers defined by temperature, giving us a three-dimensional picture of something that looked flat for most of human history, and yet enormous questions remain open. We still do not have a complete unified explanation for exactly why the corona is as hot as it is. We cannot yet fully predict when the next major solar eruption will occur, or how severe it will be. We do not have a complete model of how energy moves from the solar interior all the way up through the photosphere, chromosphere, transition region, and into the corona. The Sun is closer to us than any other star in the universe, and it still holds secrets that modern science is only beginning to crack. What is certain is that the tools are better than they have ever been. The Solar Dynamics Observatory has now been watching the Sun continuously for over a decade and a half, building a historical record that will be analysed for decades to come. IRIS continues to capture the behaviour of the transition region with extraordinary resolution, and the Inouye Solar Telescope, the most powerful solar telescope ever built, is still early in its scientific life. The images it will produce, the discoveries it will enable, are only beginning to arrive. The Sun is not a background object. It is the most accessible high-energy astrophysical laboratory in the universe, and everything it does matters. It warms our planet, charges our atmosphere, and drives the space weather environment that increasingly shapes the technology our civilization depends on. Understanding it deeply is not just scientifically rewarding, it is genuinely urgent. And the deeper we look, the more we find that our closest star is stranger, more violent, more beautiful, and more complicated than anyone imagined. If you found this video interesting, leave a like and subscribe to the channel. There is a lot more